Looking at a quantum advantage in the thermodynamics of precision in a superconducting circuits. So I am a staff scientist in the group called 22Q Lab in Chalmers University of Technology, led by Professor Simone Gasparinetti. And in this lab, we do multiple superconducting circuits experiments in which quantum thermodynamics is a very major direction that I'll be talking about. And also, we are hiring postdoc and some interns and many other positions if you're interested to join us. I will be presenting this work, which is done by our brilliant PhD student, Simon Sunderlin, who has been doing the actual measurements, and I have the privilege of being his assistant supervisor alongside Simone. And also this work is done with collaborators Mark and Khalak from King's College London and Trinity College Dublin, who are the great theorists who help us with these experiments, and it's part of our aspects consortium. So let me introduce thermodynamic uncertainty relation. It says that precision is not free. Basically, if you look at any current of a quantity, which is, for example, particles, energy, information, and you look at its variance divided by mean squared, it is bounded by this ratio given by 2 by sigma, where sigma is the entropy production rate. Basically, it means that if you want lower noise in any current, basically more precision, you require higher entropy production and more energy has to be dissipated. So why is TUR important? So it's kind of important in stochastic thermodynamics, especially when fluctuations are of the order of mean, and in biological molecular motors, where, for example, molecular motors have to move energy along a path, and there is energy dissipation along the way. So it has to also obey this thermodynamic uncertainty relation. Same thing with biochemical clocks, which regulate living system processes. And nowadays we have nanoscale thermal devices, which we can make with quantum dots or superconducting circuits, where this TUR is important. And it will be cool if we could actually violate this relation, because of course we would like to have more precision for lesser entropy production. So TUR holds for classical Markovian steady-state stochastic processes. And there are some experimentally observed violations. For example, when it is feedback-assisted processes, it has been observed to be violated, but it's also, by definition, depends on history, and therefore is non-Markovian. And then it has also been seen at transient time scales, which are not steady state. So what we are interested is when we go from classical to quantum. So can quantum coherence violate TUR? And among the many works, we would like to focus on this theoretical work from Patrick Potts in Basel, where they study a very simple 3-level measure with 2 baths over here connected to these 2 different levels. And they found out that with full counting statistics, when they calculate what is the power output into the working field along this transition versus the entropy production, they look at this ratio, the Q, which is given by the sigma variance J by J squared, something that I showed earlier. This is bounded by 2 if TUR holds. But they find in their theoretical calculation that this Q actually dips for a certain range of driving strength below 2. So they see violation theoretically. So this is what inspired our experiment, this particular way of getting quantum advantage in the thermodynamics of precision. So our approach is based on this trademark device, 2-qubit device that we really like. It's implements symmetry selective coupling between waveguides and qubits. And we did some interesting experiments a few years ago in this PRL, and then we found out that we can do some more experiments in another paper where we actually studied a similar device, and we operated this as both heat engine and refrigerator in the same device, and we measured very tiny heat currents, which were less than 1 attowatts. So now to go a step further for this work, we have to now measure actually fluctuations in this heat current to actually get that precision. That's the primary challenge that we solved in this work. So I'll quickly tell you how our device scheme works. So it's basically made of 2 qubits, which are capacitively coupled, and they are equal frequency, so they hybridize into symmetric and antisymmetric modes. And then we couple these waveguides in this particular fashion, such that waveguide S couples to the symmetric state and waveguide A couples to the antisymmetric state. And the next thing we add up over here is this dephasing noise on one of this parallel Josephson junctions, which allows us to not only change the frequency, but actually apply noise which is centered around at the frequency difference between S and A. So when we do apply that noise, we can actually transfer some energy incoherently, which allows these orthogonal states to actually mix. which means that if we begin with the state S, we can go to a mixed state of S and A with a certain dephasing rate, and it goes towards that with a 50-50 distribution, which means that it basically acts as an infinite temperature bath. So with this dephasing noise as a source, we can use this as an infinite temperature bath with variable coupling gamma phi, which is basically about what is the magnitude of the dephasing noise we apply. So now we have a different version of that device which we studied previously. So here we have, of course, the usual 2 qubits, which you can see the junction pair, basically is squid over here, which allows us to apply the flux dephasing noise. And on the antisymmetric waveguide side, we actually couple a resonator, which allows us to send in a coherent tone to drive it coherently. And on the symmetric mode side, we actually have a linear amplification chain where we measure the fields and measure the heat currents. So on the level diagram, it pretty much looks like this. So we have these 2 qubits coupled, and with this symmetric and antisymmetric modes, we are driving coherently between ground state to antisymmetric state. And with this dephasing noise, we apply an infinite temperature bar between A and S. And so what happens is that if we apply a coherent drive and then this dephasing noise, we should be able to transfer excitation from ground state to A and then to S, which then decays into the waveguide with a strong decay rate, gamma S. So first we check whether the device works. So for that we basically measure power spectral density coming out of the waveguide S. So anything that is transferred from A to S because of this dephasing noise, because of this infinite temperature bath, we should see that as emission in power spectral density. And that increases with increasing dephasing noise power over here for a given coherent drive. So it increases with this, which shows that the photons are getting transferred. And now we come to the measurements of heat currents and its statistics. So the way we measure it is actually with linear amplification chain, we measure the fields. And from that, we can actually calculate the integrated power over a certain duration t. Now, we actually do single shot measurements of QT so that we can measure the expectation value of the QT and the variance of the QT. But also because this is a very, very tiny signal floating over a very big background noise, we have to do interleave measurements where we do this with the dephasing noise and the coherent drive on and off. So once we have both the signal plus noise and the noise, we can actually subtract out the noise. So this comes down to this measurements of heat currents statistics. So this is the definition of the heat current. So this is those expectation values subtracted off and then divided over time over which it was integrated. That's the heat current, J. And then this is the heat current fluctuations, which is denoted by D, which is related to the variance. And there's a certain component which comes because of the measurement efficiency of the chain. And this is the experimental data. So over here, we have these measured values of heat current and current fluctuations in units of photons and photons squared. So we actually get a very clean data as well as the theoretical curves actually fit over here very well. And this is something we do for a cold bath temperature of about 81 millikelvin. So we basically raise the temperature of the base plate of our dilation refrigerator to achieve that. So now we can calculate what is the TOR ratio, but over here there's one more thing we have to calculate, and that is this entropy production rate sigma, which is actually also quite straightforward to measure. So basically, because there are 2 baths over here, and one of those baths is actually infinite temperature bath, so that does not contribute to the entropy production. Whereas the cold bath, you have the entropy production given by basically the heat that we already measured divided by the temperature of that bath. So we know what is the total heat entropy production rate, and that allows us to calculate this TOR ratio, Q. So over here, we focus on the circular symbols, which is performed at 81 millikelvin. A zoom in over here, we see that this ratio does go below that bound of 2, right? And the standard, these are twice the standard deviation over here, so it's actually quite below that 2. On the other hand, when we look at a similar data set, but done at a different TC temperature of 31 millikelvin, it actually does not really violate that bound. And also it matches both of this, our experimental data actually matches what we predict theoretically. So in summary, in this work, we basically do what we believe is the first time measurements of fluctuations in heat current with microwave photons. We see an experimental observation of the violation of the thermodynamic uncertainty relation using quantum coherence. This is something we think we could also use as a thermodynamic witness of quantum features in such quantum thermal machines. And an outlook is that, okay, we could probably also build a quantum refrigerator where we could make a useful quantum refrigerator where we have a precision advantage. With that, if you would like to know more about this, visit our website and LinkedIn, and also you can contact us. And once again, we are hiring more people to join our group. Thank you.
You do have time for questions. If not, I do have one. You do have steady state PUR as your figure of merit to violate.
Yes.
But then the couple of calculations you show us is you integrate it over some 3 microseconds or something of that sort. Would it be also possible to compare with finite time PURs, which are different from steady state PURs?
So if we want to see the violation, I mean, if you want to really compare, we would like to compare it with the steady state. And in this case, 3 microseconds is long enough to be steady state because the other time scales are actually of the order of some hundreds of nanoseconds. But if we do find that at a lower time scale, we cannot really claim if we have violated it.
No, I do mean there are other versions of PUR known as finite time PURs.
Yes.
Which are tighter than steady state.
Yes. Yes.
Would it be possible to also test whether they violate that?
I think so, yeah.
So what do you mean by this outlook and the precision advantage? What are you aiming at? And the last.
Yeah. I mean, also when we are trying to cool down with the quantum refrigerator, there is a certain cooling power which is also fluctuating, and therefore with this, there is a certain entropy production that is also occurring. So basically, to make the refrigerator more efficient. Yeah, stable.